Okay, for step 2 here, we're going to go ahead and create our model. This should hopefully be the quickest part of things. Getting the training data and everything sorted there, that's the difficult part. Configuring a model, nice and quick. So, we're going to grab TensorFlow. We have our spectrogram size of 512, 512, and 1, and our number of classes. And after that, we just need the layers and the models from Keras. And then we have this map function right here. So since we're using TF records, we have to parse the data back out of the TF record. Pretty much just telling the function what it looks like. And this is really similar to what we used before when we were writing the record. We have a dictionary here for the feature. We have the same keys, class and spectrogram. Except this time for the value here, we're setting it a TF-IO fixed len feature. And the class is just 1 because we know that there's one value there. And for our spectrogram, we know that there is, 512 times 512 values there, right? Because we flattened it out. So it's the 512 by 512 spectrogram, but it's all in a row. One dimension. So that's the size of the spectrogram. Then we create this example here by parsing out that serialized example using that spec that we just wrote. The spectrogram is the value at the spectrogram key, and we're just reshaping it using that same 512 by 512 by 1 shape. The label, we're just recasting it to N32, and then we're spitting that back out. So we define that function here, and then here's where we're going to use it. We're creating a data set from our list of files. The list files part, you can just use a glob and grab everything inside of a folder, and then we're repeating it there. So it's just going to treat like we have a never-ending supply of these TF records. And then for each serialized example that it reads from that record, it's going to pass it. Actually, for each file name, it's going to pass it into the TF record data set, which will then be able to allow us to read out the serialized examples, which is what we'll pass in here to the map function. And then we batch it into 16, a batch size of 16. Anyway, from there, we're just going to start building our model using the model API here. So we have an input layer, and we're going to assign an m in, and then we're just going to use the variable m for like the inside of our model. We're setting in filters 16 here because it's really simple. We just have multiple layers of two-dimensional convolutions, and then each one is going to have 16 filters. And everything here we're using a size of 2. So 2 by 2, 2 by 2, 2 by 2, and 2 by 2. And then we're assigning a 64 unit dense layer to each timestamp after that final max pooling. Before we flatten it back out, removing that last dimension, and then adding one dense 256 unit layer, and then one more for our output. So this is going to be in classes long. It's just a softmax activation because we're looking for a probability distribution of which class is coming out of here. Okay, so we build the model here, just saying our inputs and our outputs. That's why we assigned it to different variables. I don't know why I used the underscore for one and not the other. It's a mystery. Alright, model.compile. We're setting our loss function here to sparse categorical cross entropy. That's because we're expecting one output from a multi-class classification, or a single class classification. Using the Atom optimizer, and for metrics, sparse categorical accuracy, just so we can see how accurate we are. Here's our summary of our model. We can see how we start with the 512 layers, move down to 256, and 128 and 64 after that, and we just keep going down until our final max pooling layer is where we're at 2216, and then applying that 64 unit dense layer to both those two sides. Pretty much, I guess it gets split into two by that point. Flattening it back out, applying that 256 dense layer, and then our final 105 wide softmax layer. After that, we ended up running this on a box of the GPU, so we're testing if the GPU is there. You can do that with tf.test is GPU available. True, it is. Then we fit the model there, just dividing the steps per epoch as 1,000, so that way we could see a nice little jump around. We ended up around 50% accurate after training, what was this, 10,000 times. So it worked enough that we were able to go back through with use this model to go back through and reclassify our data for the next step of the sound event detection. So yeah, right here we save it, Florida birds at H5, which we can later pull up to go through and reclassify all of this data. So nice and quick. The smallest notebook, probably the quickest to talk through. The model is really simple. It's not the best, but it works enough to get us to this next step here. And later on we can improve this. This is, just this first step. So that's our convolutional neural network to classify the spectrograms that we have coming in from TF records using a data set.